Okay, in this video, we are going to add one of our two remaining pieces that we still need to add to our model here to have a more or less complete model of simulating vertical jumping. We're going to add passive joint moments to the model. Now, the motivation for this is that, if you remember the kind of motion we're getting out of our model now, here I'm going to simulate a fairly contrived case that starts with the model hanging in space with no gravity, and both of our muscles in the model, the glutei hip extensor and the vasti knee extensor, are going to be active to their lowest possible level, to 0.1% activation. So they're going to produce some small moments in the direction of hip extension and knee extension. The model is going to begin from an initial flexed posture here, so it's going to start with 45 degrees of hip flexion and 45 degrees of knee flexion, and then the muscles are going to produce small moments in the other directions. So we should see the hip starting to extend from this initial flexed posture, and the knee also starting to extend from this initial flexed posture. And in our model in its current state, let's see what we get there. So hip is extending, knee is extending. Real knee should stop right about there, and you can see ours keeps going. Okay, let's watch that again. A real knee should get into full extension here and should stop, and ours does not. Ours keeps going. Okay. The reason it keeps going there is because we have an incomplete model here of the resultant moment at that joint that governs the motion of that joint. We have the contribution to that moment from the active muscular forces, the forces in the muscles due to activation of their contractile machinery by the nervous system. We do not have in here a model of the passive contributions to that moment. The inherent passive stiffness of the muscles that get stretched as we move these joints, and the conceptually similar contributions to things like ligaments that get stretched based on the posture of the joint, and the articulating surfaces of these joints that come into contact at certain poses that all affect the overall net moment at this joint and limit the ranges of motion the joint can practically go through. Okay. None of those latter things we're accounting for here right now. All we have is a contribution of the active muscular forces. So the reason our knee keeps hyperextending here to well beyond normal range of motion is that there's nothing in the model telling it what a normal range of motion is. In our model, this is just a simple hinge joint, and there's no physical reason why it would stop there in full extension and not keep going into hyperextension like it does here when it gets beyond a normal range of motion of a knee joint. So basically, we need to add something telling the joint that, hey, you can't go beyond full extension here, even if your your active muscle forces are producing moments that want to move you beyond full extension. Okay. So how do we do that exactly? I'm going to add some things here to the model and show you the effect, and then I'm going to explain what I added and why I added it and where it came from. So bear with me here for a second. In our model state equations here, we implemented our muscle model by looping over both of our muscles here. At the end, we calculate an SEC force, a force in the SEC due to activation of the muscle's contractile machinery. We take that force times its moment arm to these respective joints, the hip joint here and the knee joint. We add that active muscle moment to the resultant joint moment, which initially started here at 0. And then out of that, we get the resultant moment at the joint. Now here, inside this muscle model loop, we are just computing the contribution to that moment from active muscle forces. So let's update our label here. We're updating joint moments specifically for contribution from active muscle forces. Okay. Now here we also, to make our model motion and joint kinetics a little more realistic, we're going to update our joint moments for contribution from passive joint structures. So just like I did up here, where I'm including the contribution of my active muscle forces, I'm going to take my joint moment, and I'm going to add something to it. And same thing here for my other joint moment. Oops, sorry. Should be equals. I'm going to take my moment at the knee and add something to it. Okay? And what is that something? I already tapped it out here before class. I'm going to go grab it and just paste it in there and show you the consequences of it. And then we will explain what it is and where it came from and why it works the way it does a little bit later. Okay. And I've also got some new parameters here for passive joint structure. Let's add that to our muscle model to our model parameters here. There we go. Okay, I'm first off going to comment these things out and remind you what things look like without the passive joints. You get a motion like that. Not very realistic. Too much knee hyperextension, way too much. Now, let's turn my passive contributions on and run it and see what we get. And now my knee stops before hyperextension. Now let's turn my muscle bang on times to be banging on within the simulation time here, so that at 0.8 seconds I'm going to extend my hip as hard as I can and extend my knee as hard as I can. And let's see what happens here now. Okay. You can see there at the end my muscles banged on there, but they were limited in their range of motion. You can see here my knee got into, if you look closely, a little bit of hyperextension, but not too much hyperextension. Okay. Now, what's happening there is not that my knee extensor moment from my maximally activated vasti is suddenly going away and is not contributing anymore. It's very much contributing. But now I also have a passive contribution acting in the other direction that's countering out that large extensor moment from the vasti muscle, giving it a net moment of 0 right here, so that the knee is no longer moving. Okay. So that is what's happening here by adding this passive moment here to the hip joint and this passive moment here to the knee joint. When the joints get to certain positions, these functions that I added here, these exponential functions, if you look closely, are producing moments in the opposite direction of these active muscle moments up here that are balancing them out, balancing them out, and producing moments in the other direction so that the joint cannot get into unrealistic ranges of motion. Technically it could, but it would take tremendously large unrealistic muscle forces to move the knee here into appreciable hyperextension. So these passive moments that I added here are essentially restricting the range of motion of the joints to physiologically realistic ranges here. Okay. Now, what is the motivation for adding these things? It's restricting my joints to realistic ranges of motion, but what's the physiological, structural, anatomical, functional motivation for adding these things, other than it gives me a visually more realistic looking motion of my model here? To motivate what I just did here, before explaining where these particular expressions came from, let's look at a little bit of underlying theory here on why we want to add any particular expression here that accounts for contribution of passive joint structures to the moment there. I'm going to pull up one of our earlier readings from class, the Crown and Shield and Brand review article. So this one here, Prediction of Forces and Joint Structures. If you scroll down to figure 3 here, I think, in this paper, this one, this is a famous figure in biomechanics. This is showing the relationship between resultant forces and moments at joints in the thick black lines and internal structural forces at joints in the smaller, thinner lines. Okay? So these big thick lines, this one Fk would be the resultant force at the knee, this one Mk would be the resultant moment at the knee. These are the kinetics that we typically calculate with inverse dynamics, for example. With inverse dynamics, we would calculate these resultant kinetics from the external loading of the body, things like ground reaction forces and gravity. Internally, these resultant kinetics are also equal to the vector sum of all these internal structural forces inside the joints. These little tiny arrows, the FMs, there's an FM1, FM2, all the way to FM10. Those are forces in muscles that span the knee joint. There's an FL 1 through 4 for the forces in ligaments at the joints, or at the knee joint here. And there's FC here, contact forces between the articular contacting surfaces of the joint. So muscle forces, ligament forces, contact forces. This Fk, this resultant force at the knee, would be the vector sum of all 16 of these little internal muscle, ligament, and contact forces. So if I add up all of these little skinny force arrows here, they would add up to this big black Fk arrow here. Similarly, if I took all of these internal forces in all of these 16 structures, multiplied each of them by their moment arm to the rotational center of the joint here, and added all of those individual moments together, they would add up to Mk here, the resultant moment at the knee joint there. Okay. So here we have shown muscle, ligament, and contact forces. More broadly, you could think of these resultant forces and moments at the joint as being the vector sum of forces in all force-carrying structures at the joint here, not just muscles and ligament and contact, but any structure at the joint. The capsule that surrounds the joint internally, the skin that surrounds the joint externally, all of those things would carry some non-zero force that would contribute to the resultant force and moment at the joint here. In biomechanics, we tend to assume that muscles and ligaments and articular contact account for the vast majority of these resultant joint kinetics. And so we tend to ignore things like the tension in skin and assume that the resultant kinetics at joints are fully due to muscle forces and ligament forces and contact forces and things like that. Okay, how does this motivate what I added to my model there with those functions for passive joint moments? Right now, we are only modeling the contributions of muscle forces to this resultant moment, and we're only modeling a portion of muscle forces. In particular, we are only modeling the active component of muscle forces, the component of muscle force due to activation of the muscle's contractile machinery by the nervous system. Muscles will still carry some non-zero force even when the nervous system is not activating the muscle at all, due to the inherent material properties and passive inactive stiffness of the muscle due to the material the muscle is made of. Kind of like if you take a rubber band and stretch it, the further you stretch it, the more and more force it'll develop because the rubber band has some stiffness to it. Same story here with muscles and tendons. The further that you stretch the muscle, even when it's inactive, the more force it will carry in that muscle due to the passive stiffness of that muscle. There'll also be an element of velocity here. The further you stretch the muscle, generally the more force it'll carry there. And also generally the faster that you stretch the muscle, the more force it'll carry there, due to muscle having a large amount of water inside of it normally, and that water adding an element of viscosity there that'll make the passive rate of stretch of the muscle also affect the passive force in the muscle. Okay. That argument would extend not just to muscles, but also to the ligaments here at the joint and to the articular contact surfaces at the joint. Depending on the pose of the joint, the flexion-extension angle of the joint, these different structures would be stretched or compressed to different lengths and would be stretched or compressed at different rates of change in length. And this would affect the forces in these structures, the passive forces in these structures, which would affect their contribution to this resultant force at the joint and their contribution to this resultant moment at the joint. The resultant force we're not worrying too much about in this class. This is very important when we get into modeling the loading of joints, but we haven't done much of that in this class. We're mostly just dealing with the motion of the joints, which is, for pin joints, for simple rotational joints, is due to this resultant moment at the joint. Okay, let's do another kind of visual example here, motivating the inclusion of these passive contributions of joint structures to this resultant joint moment. Okay. So without adding the passive contribution here, again, I'm only modeling the active contribution from muscle forces, and from that there's nothing limiting the range of motion of my joints. So let's do a visual example here of how passive contributions from joint structures limits the range of motion of my joints. I will pull up my video here. And hey guys, and I'm going to have a hard time showing you my knee here. That'd be kind of awkward, but I'll show you the upper limb version of the knee here, the elbow. So here's my elbow joint. I can extend it using my triceps. I can flex it using my biceps. And I can move through a certain range of motion here. Okay? In the middle of my range of motion, there's not a whole lot of resistance or not a whole lot of stiffness of my elbow joint there. I can activate my triceps and extend the joint. I can activate my biceps and flex the joint, and not a whole lot of resistance to either of those motions. Okay? If I start with the joint flexed here and then activate my triceps, the triceps will produce an extensor moment at the joint that will extend it. So I'll keep going, and then suddenly I stop. Okay? So what happened there when I stopped, when I'm not able to go beyond full extension here at my elbow, or to go into hyperextension here at my elbow joint? Why can't I just keep extending there? It's not because my triceps stopped producing force and stopped producing an extensor moment there. They're still active, they're still producing force, and that force is still producing an extensor moment at that joint. But for the joint to not be moving here, the net total moment at the joint, the resultant moment at the joint, has to be 0. So meaning whatever force or whatever moment my triceps muscle force is producing here in the extensor direction has to be balanced out by a flexor moment in the other direction. Now, where is that flexor moment coming from that's making this resultant moment 0 right now? Well, it's coming from the passive contribution of other structures in this joint. Okay? Now, what are those structures? Well, as I'm extending my elbow here, my biceps crosses the other side of the joint, and as I'm extending the elbow, I'm stretching the biceps. It's getting longer and longer, and just like a rubber band, as I stretch it further and further, it produces more and more passive force. Same story here with my biceps. As I stretch it further and further, it's producing more and more passive force and a larger and larger passive flexor moment, counteracting that active extensor moment from my triceps there. Okay. Now, there's other contributions there to a passive flexor moment near the end of my range of motion that are arguably more important than the contribution from passive stretch to the biceps there. As I get near the end of my range of motion, there's ligaments here in the elbow that get stretched quite a bit and produce a flexor moment in the other direction. And there's also articular surfaces here in the bones of the joint that come into contact and end up producing a flexor moment in the other direction. Okay. Oh, there's a siren coming by, sorry if you guys can hear that. So those passive contributions that end up producing moments typically in the opposite direction of the active contribution from the muscle group that's moving the joint are what limit the range of motion of my joints. Sorry, I'm going to let this go by. My dog might also start howling here. He likes to howl at sirens. You going to howl, buddy? No, thank you. Thank you for not ruining my video. Good boy. Okay. So what I just described there would be what we would think of as a lumped parameter model of passive joint stiffness, where I would be kind of looking at the whole joint level contributions of all of these structures on the whole to the passive stiffness of the joints, or the tendency of all of these structures together to be producing a certain passive moment at the joint in certain postures of the joint. I could, in theory, go into my model and replace my single knee extensor muscle with a whole bunch, individual models of all 10 of these muscles, all 4 of these ligaments. I could make a real complex model of joint anatomy and geometry here and model these contact forces. That would technically be a more realistic model. It would also be much more detailed and much more complicated, and it would need individual passive stiffness relationships for all these structures and resting unloaded lengths and things like that. So it'd real quickly get real complicated. So what I added here to the model down here, where I'm updating my joint moments for contributions from passive joint structures, is I'm modeling this passive stiffness at the joint level. I'm not modeling it at the individual muscle or individual structure level. And this is just simply a simpler way of achieving this goal of limiting the ranges of motions of my joints to physiologically realistic ranges without adding the complexity of modeling the passive stiffness and damping of individual structures inside the joint. So it's kind of like I'm combining all of these things together into their kind of net combined contribution to the passive component of this resultant moment here, which allows me to avoid the complexity of modeling individual passive characteristics of all these structures. There's certainly research questions where that would be interesting and would be important and perhaps necessary to do to model the passive structural characteristics of individual particular structures of the joints. But for our purposes, where we, in this fairly simple model, just want to limit the model to realistic ranges of motion, we'll take this simpler joint level approach here. Okay, so we have our model here for passive joint moments and joint resistance at certain ranges of motion. We have our motivation for including this at the joint level. Now, what did I actually add here? What is this? You can see some exponents here. You can see some new parameters here. You can see our state variables for joint angles, for the knee angle there, Q5, and the hip angle, Q4, and then I've got my velocity terms over here. Where did this function come from? What is this? This comes from a new reading. That particular function comes from a new reading that I uploaded. It's a well-known paper on passive joint stiffness by Reiner and Adrich. Reiner and Adrich, 1999. And their paper here is identification of passive elastic joint moments in the lower extremities. Okay? What they were doing here was similar to what I was demonstrating on my video here. Let me pull my video back up here. Where, depending on the pose of my joint here, at different angles, the different structures inside my joint here, in the absence of any activation of the muscles by my brain, at different angles of the joint here, the different structures spanning and comprising that joint will be stretched or compressed to different lengths and will be producing different passive moments in whatever direction at that joint. Okay? And so ideally, if I want to create a joint level model of that passive moment at the joint due to the length and the stretch in those different joint structures, I would want to measure the angle of the joint, probably across the full range of motion, and I would want to measure the passive moment at the joint at each of those different angles. Okay? We can do that with devices that we have in biomechanics called dynamometers. you'll often hear those devices called a biodex. Biodex is just the company that makes a popular dynamometer. We have a biodex machine in our lab in the SPH building. But if you hear it called a biodex, that's really just a commercial name of a company that makes a device called a dynamometer that can measure the torque produced at joints at different contractile conditions, at different poses of the joint, at different velocities of the joint, when the joint is passive, when the joint is active, etc. So a machine allowing you to measure moments at joints under different kinematic conditions and different contractile conditions. So that's what they were doing here in this Reiner and Adrich paper. They had subjects on a dynamometer-like device where they then put the joint into different positions and measured the position of the joint and the passive torque at that joint in those different postures. That's what they're referring to here by passive elastic moments in the lower extremities. They did this at the hip joint, at the knee joint, at the ankle joint. In particular here, at the set of different postures of the joints that they measured here, they were accounting for the fact that some of the muscles in the leg here cross multiple joints, or some of those muscles are what we call biarticular muscles that span two joints. For example, at the hip and the knee here, the hamstrings span both of those joints, so the passive stiffness of my hip will depend not just on the hip angle, which stretches the muscles and ligaments and things there, but also on the knee angle, which stretches the hamstrings and changes how much force it's going to produce and how much that force is going to contribute to the moments, not just at the knee joint, but also at the hip joint simultaneously. Okay. Same deal on the other side of the joint there, those joints there. There's a muscle called rectus femoris. That's a hip flexor and a knee extensor, and so it'll contribute to the stiffness of the hip based on the knee pose and the stiffness of the knee based on the hip pose. Okay. In the calf here, there's a muscle gastrocnemius that's both a knee flexor and a ankle plantar flexor, and so the moment at the ankle depends on the knee, the moment at the knee depends on the ankle. Okay. So in Reiner and Adrich here, they used a dynamometer to measure the passive moments at the hip and the knee and the ankle at different combinations of angles at the hip and the knee and the ankle. They measured all of those data, all of those moments, and all of those angles, and then they fit some mathematical expressions to them that were chosen to have an exponential form simply because that form fit these data well. It appeared to, in most cases, be a double exponential looking relationship between the angle of the joint and the passive moment or passive torque at that joint. Okay. So this is an example of the model that they produced here for the passive moment at the ankle on the y-axis as a function of the angle of the ankle across the full range of dorsiflexion and plantar flexion here. You see two curves on here, theta k here 60 and theta k here 0. This is showing the passive torque angle relationship at the ankle with the knee at 0 degrees of flexion in this curve here, and also with the knee at 60 degrees of flexion in this curve here, accounting for that contribution from the biarticular gastrocnemius muscle, which spans both the ankle and the knee. And so the pose of the knee affects the passive stiffness of the ankle through that gastrocnemius muscle. And you'll also see this here in their model of the passive stiffness of the knee, where it depends on the hip angle and also on the ankle angle, which they don't show here. And also their passive torque angle relationship here for the hip, which depends not just on the angle of the hip, but also on the angle of the knee. Okay, so those expressions that I pasted into my model here, down where I am updating my joint moments to account for passive contributions from joint structures, those are these expressions here from Reiner and Adrich, which are defining the passive moment at the knee joint and the passive moment at the hip joint. Okay. I went ahead and did this outside of class on my own rather than having you guys do it because it's kind of a pain in the neck. the directions that they define their joint motions here in this paper are for the knee are not the directions that we need in our model. And also some of these parameters here, some of these coefficients in these expressions are in terms of degrees for these angles or these angles, and we need them in radians for our model. So I went ahead and did those conversions here before class and included them in the signs on these expressions here and in the values of these parameters that I defined here. Okay. We also added in a damping component there with a small a damping coefficient there that is tacked on to the end here of these passive moment expressions. That's accounting for the fluid content of these structures and the viscous component of passive joint moments there. Okay, so with these moments added here, we now have realistic, or at least more realistic motion of our model. When we're in a passive state here, we don't go into full extension, and even when we blast on our muscles to max capacity there, we aren't able to hyperextend the knee by too much. So a more realistic model of passive joint motion there and passive joint stiffness. We still need to add foot ground contact, and we still need to revise our initial states of our model to get it into an initial squatted posture, and then we will be ready to jump. So we will launch into those final two tasks next time.